All right, we're gonna have a discussion on the Ansys workbench workflow with this Evo fender right here, which is fiber filled. Here we are in Ansys mechanical, and we have a look at the fender. You can see the mesh. We're gonna export this mesh from workbench by using the tools write input file. And Advanced Material Exchange will accept a variety of Ansys input files like CDB, INP, and DAT, and we're gonna export a CDB file specifically here. Then we'll bring it into Advanced Material Exchange on the screen. The same CDB file that we exported we'll bring in as the structural model, which we'll see here. We'll select the units for the model, and then we'll select OK. And then we need to bring in the mold flow model. We've ran this mold flow simulation previously. This is a mid-plane mold flow simulation and a shell structural model. So here we are with the mold flow results, and we're going to map the data between these two fenders. So we want to map the fiber orientations, and then we're going to view the fiber orientations. And you're going to note that the colors are a little bit different on these two. That's because the structural mesh is not as fine as we need it to be. But you can see we can step through the bottom, middle, and top layers and view the fiber orientations for the thickness. We're going to choose our material behavior, which is elastic plastic, and we're going to add the data by selecting a CSV file, which contains all of our material data, and it'll automatically populate the screen for us. We'll plot the data so we can calibrate all of our material constants for the nonlinear simulation. And once calibrated, we'll show the fitted curves, the experimental curves, and all we really need to do is just export our new CDB file that we can run in Ansys, which we'll be showing right here. Great. So now we're on our desktop, and Autodesk Helios PFA automatically ships with a command prompt that's bolted onto Ansys. So all we need to do is navigate to the folder where our Ansys files are located, and then we can simply type in a command called Ansys Helios, and that tells Ansys to link up with Helios. And all it requires, which we're highlighting here on the screen, is the Ansys Helios command, the version of Ansys you want to run, and the file name, whether it be a DAT, INP, or a CDB. So we're going to choose our CDB in the folder that we navigated to right here on the screen and hit enter. And then now we're back in Ansys Mechanical. And what we're going to do then is just input the results, which are saved as an RST file. So we'll select solution, and then we'll import those results in a form of RST file. Select our unit set and move forward with that. Ansys will automatically read these in and apply it to the geometry that we had in our workbench file. And then what we're going to do is we're going to create what we call a user-defined result. So Helios tags along what we call SVARs, which are user-defined state variables. And right here we're going to plot SVAR11, which we call it, which is the matrix effective stress and gives us an indication of plasticity. So we've actually constrained this part how it would be constrained on a car, and we're pushing on it like somebody's putting their knee into it and showing the deflection. And you can see we're actually showing the effective stress. You can see the effective stress grow, and then it'll buckle. And it's buckling because we've applied so much force, it's actually breaking. So here we've stopped the simulation. We're showing what that effective stress looks like through the thickness of the part. And finally, we're going to plot the displacement by just selecting solution again, and then adding a total deformation. And we're just showing this displacement at a specific point in time before that global buckling. But you can see here's the displacement plot from applying that static load.